simulation of both strings with model synthesis. And this work was done together with Michele Ducceschi and Stefan Bilbao. And it was supported by the European Research Council under the NEMUS project. So, both string simulation is a classic topic in musical acoustics and sound synthesis. And first studies were conducted by Helmholtz and then Raman back in the days. And they discovered that essentially strings bowed in a musical way moves in a way called Helmholtz motion, which is represented here in this picture. Also, they found out that the force is linked to a friction coefficient phi, which depends on the relative velocity eta between the bow and the string in one point. And over time, many different models for this force were developed, and we can see some of them here in this picture. For this work, we used the one in bottom right, which is a curve that was proposed by Bilbao. And this has the advantage of being continuous, contrary to the other models, as you can see. And extended work on finite difference simulation of both strings were done by DAFx and Bilbao. However, their algorithms require iterative routines to work, such as Newton-Raphson. And these methods are generally a bit computationally expensive because they require to iterate multiple times per time step for finding a solution. The existence and uniqueness of solutions is not always guaranteed, and also there is the problem of the choice of the tolerance threshold. So, in 2021, Ducceschi and others proposed a non-iterative numerical solver for the simulation of nonlinear ordinary differential equations, ODEs. And this work investigates the application of this numerical method to the problem of both string simulation. So let's start with a simple case, one-dimensional case, the bowed mass. Here we can see the scheme of the system. This is an oscillator with a bow that excites the system. And of course, this system is described by a second-order ODE in time. Here we have that phi is the friction coefficient, the continuous one we saw in the previous slide. U is the mass displacement over time. Omega 0 is, of course, the angular frequency of the oscillator. Vb is the bow speed, and Fb is the bow force normalized by the oscillator mass. And notice that phi satisfies these properties, which are fundamental for the numerical method to work. So, since this solver applies to first-order ODEs, we need to rewrite this equation in first-order form. We need to define a generalized coordinate q, a momentum p. We then have an energy of the system in this form. And the system equation can be rewritten this way. This is now a two equations system. We have a state vector x, and the matrix J is skew-symmetric and has a form which is typical of port Hamiltonian systems. Now, to simulate the system, we can use finite difference operators, and I know you already know all this, but let me do a brief introduction on what they are. So we first define a sample rate fs with a sampling step, constant sampling step k, and we'll have that the continuous function u of t will be approximated by a time series u of n at time steps tn, where n is an integer index. We can then define the difference operators this way, given time series x of n. We have the shift operators, backward and forward shift. Then we can define the difference operators, which are approximations of the continuous derivatives, and we can then combine them to obtain higher order derivatives approximations, such as we can see here. Also, we can define mean operators, which will turn out to be useful, as we will see later. And then we can now simulate the system. We have many different ways we can take to do that. We can, for example, directly substitute the continuous derivatives with difference operators, like this. We can, for example, use the midpoint method for discretizing the first-order system. And it can be proved that both these systems are conditionally stable, so passive, and second order accurate. This can be proved. However, we can see that the unknown appears inside a nonlinear function. So these two systems are fully implicit in that they require Newton-Raphson to work. Now, on the other hand, if we follow the paper by Ducceschi, we can write a non-iterative solver this way. And here we have that sigma is a factor that allows to obtain a second-order accurate truncation error. We have that the discrete energy gradient takes now this form, and the proof is in the paper. And also we have that, we can see that now the nonlinear function is evaluated at time step n, so this method doesn't need iterative solvers to work. So no Newton-Raphson, anything, just a simple matrix inversion. So this makes this algorithm very efficient. But let's see how this scheme behaves. To check this, we run a solver comparison. First, we defined a reference solution, which was the one obtained with the second-order system scheme, run with an oversampling factor of 30. And then we defined the error as the difference between the outputs of the schemes and the reference solution. We also included forward Euler, this explicit integrator in the test, because it's explicit as the one we're proposing. And then we run the test with all the solvers we saw in the previous slide. We can see that forward Euler shows an error which is greater by some orders of magnitude with respect to the other solvers. On the other hand, the non-iterative scheme, the phonit scheme, behaves just as the other two schemes, the ones that require Newton-Raphson. And if we increase the bow pressure, then we see that forward Euler explodes, shows instability, and also that the non-iterative method still displays a robust numerical behavior, just as the other two schemes. So let's now move to a distributed case, so the Bode ideal string. This is another image that represents the system, and this is the equation that represents the system, that describes the system. And you know this is second order PDE in time and space. We have that U is the function of space and time that represents the string displacement over time. L is the string length, as XB is again the input point. C is the sound speed. FB is again the bow force normalized by the total string mass. VB is the bow velocity, and here notice that the Dirac deltas indicate that the force is directed pointwise. So to simulate the system, we can both use difference approximations of spatial derivatives, because we need to turn a PDE into a system of ODEs. And using difference approximations allow us to do that. Or we can use a model expansion. And in the paper, we used both approaches, but here I'll focus on the model expansion for lack of time. So let's assume a model expansion for U. So U is expressed as a superposition of model displacements. Then we have that the model shapes are the one obtained with the Dirichlet boundary conditions. Then we can substitute this solution form into the original equation, and this is what we get. Then we perform model projection. We calculate the integrals, and this is the result we obtain. Here, omega is a diagonal matrix of eigenfrequencies, and I ran a bit fast on this slide, but if you need more info on the model expansion, you can reach me out, or you can ask me later. If we solve the integrals in the unforced case, this is what we get, and this is a system of uncoupled oscillators. Now let's see what happens if we introduce forcing. And we still have a linear part of uncoupled oscillators, but we now have a coupling given by the bow in the form of a dense matrix. And so solving a system of uncoupled oscillators is very efficient, but solving a dense system is not that efficient. So we're losing efficiency here. However, we'll see that by applying the non-iterative solver and exploiting the structure of the matrices that come out, we will still be able to obtain an efficient solution. We, again, need to rewrite the system in first-order form, so we define the generalized coordinate q and momentum p. These now are vectors. We still have our state vector x and an energy which now has vector form. And this is the same equation we had for the mass, but this time this is a large system of equations. And notice that J is skew-symmetric, again, and block diagonal. And this will be very helpful later. So a non-iterative solver for this scheme has this form. This is, again, very similar to the expression we saw for the mass, but this time this is a large system of equations. But now we can expand the operators and solve for the unknown, which is the state vector x at time step n+1. And we can now see that this method doesn't need any iterative solver. We can simply need a matrix inversion. So we're avoiding the use of iterative solvers. We can simply solve this system with the matrix inversion, and this system is called linearly implicit. However, the matrix we need to invert is dense, and inverting a dense matrix is not necessarily an efficient task. So we are not using iterative methods, but we still don't have efficiency yet. But let's see what's the form of A. So we can define matrix T and vectors A and B, so that we can rewrite the matrix A in this form. And so A is now expressed as the sum of an invertible matrix T plus a rank 1 matrix. So we can exploit Sherman-Morrison formula for inversion. So we now only need to invert the matrix T. But T is block diagonal, because J was block diagonal. And so we can use a block LU factorization to invert each block at a time and obtain fast inversion. So we're back to efficiency. Now, let me quickly add damping and stiffness to the model. This is an Euler-Bernoulli model for the string. If we perform a model expansion of this model, this is what we get. We now have a different form of eigenfrequencies, but it is exactly what we had before. Here, C is the diagonal matrix with the model decays. So the model expansion allows for a very fine tuning of frequency-dependent damping profiles. Some results. These are different vibrational regimes. Plots on the same row are snapshots of the same waveform. We can see that in the first row we see multi-slip motion. And in the second case, we can see that the string reaches Helmholtz motion after a few seconds. Some benchmarks. These are runtime over real-time ratios. So since these numbers are all below 1, we can see that the algorithm runs in real time, even in MATLAB, and for high sample rates. So it's very efficient. Now, to conclude, I wanted to let you hear how this sounds after all the equations. And these were the 4 cello strings, and now I have an arpeggio. And finally, if you want more information, you can go to GitHub. This is my GitHub. There is the repo for this project here. And you will find MATLAB code and in the various versions and other sound samples. And yeah, I think I can stop here. And thank you for your attention.
Okay, thanks for the presentation, Riccardo. We have time for a couple of questions.
Simple question, just microphone. Not for me, but for the stream. From judging from the example, I feel a lack of friction in the sound. It's very low pass, let's say, very smooth.
Yeah, it might have to do with the way the examples were processed, but also the focus here is more on the numerical method, you know, rather than on an accurate model. So we also use the linear string, and we don't have different polarizations of the string, but the focus was mainly on efficiency of the numerical method and see how this previous developed method could be applied to both strings.
Okay.
Any more questions? Yes.
I wanted to ask, because this method was designed for efficiency, then how long did the simulation take to synthesize this arpeggio example?
So I showed a benchmark, and you could see that the benchmark I saw, the numbers I showed, were runtime over real-time ratios. So we divided the runtime time over the real-time time request that we wanted. And since the numbers were below 1, well, I can say that the algorithm ran in real time. So, yeah.
Any more questions?
So this matrix T that you invert, it doesn't change over the course of the simulation, right? It just, you can fix it at the start or not?
No, it doesn't. I mean, it does if you change parameters of the string, like string length, or other parameters, but the tension, for example, because it contains the eigenfrequencies. So yeah, it does change if you want to, for example, change the length of the string to apply, for example, a finger on one point, but yeah, otherwise it doesn't. And it doesn't change the structure. That remains fixed.
Is the follow-up question, is the length of the string in the arpeggiator thing, what you showed, is that the parameter that is changed in real time, or are it all different strings?
All different strings.
Different strings,
yeah,
okay, okay,
yeah,
thanks.
Maybe one last question. Okay, thank you, Riccardo.
Thank you.